single day. I'm gonna make something great. That's my way.
I had made slides earlier on this topic, but I realized they were not so perfectly done. So I'm going to use the PDF format that I devised, and we're going to follow it from this PDF. I hope everybody is able to see it. So basic control circuits show us how the two methods or the two types of control circuits that exist and that we use for us to understand how we can control a system. This topic, first we define what is motor control, which is simply controlling the basic functions of motor operation. And these include the starting, acceleration, speed, protection, power, reversing, and stopping. It's very important. Each element has got a function where it is applied. So for starting, we're going to look at specific starting methods for AC motors, for DC motors, and so on. Acceleration also comes in when we start looking at speed control. Then speed, of course, we look at variable drives, we look at variable frequency drives, variable voltage drives. Then we also have power, reversing, and stopping. So in a case where there's a system that is operating and then we need to stop that system because we see something malfunctioning, then we have to have a means of stopping that operation or that motor running. And that is where our motor control comes from. And in these basic circuits, you are going to have what we call the basic functions for a complete motor controller. So it has to have at least 4 basic functions, one of which is to have overload protection, which is the number 4th point. And then you have the means to start and stop a motor. Like I mentioned, in many cases, if we see something happening, we need to stop that motor from continuing to run or damage some equipment. Then we have to have short circuit protection incorporated in the system. And also we have to have means to disconnect the complete motor branch from the feeder line, meaning we have to have ways of isolating even from as far as from the fuse section before the contactors, before the overloads, before the motor itself. So that whole branch that is holding on to the motor we must have means to isolate that branch. We have 2 types of controllers, what we classify as electric controllers as well as manual controllers. For instance, electric controllers, you have predetermined operation where you set a system, you run it, and it's running automatically. And it's repeating, of course, certain processes that are already pre-installed or programmed in a case where you're using programmable logical controllers, PLCs. And then we also have manual control where a controller or a human being in this case goes on to do certain actions, to perform certain actions to control the motor. For instance, if you visit the mines, we have what we call the winders. Operates as a winder controller. In the mines previously used to be very manual. Most of the modern ones have been made into automatic operation. But there's a controller who sits there and ensures that it can see up to which level the winder has gone and stops or pushes the button to stop the winder so that the miners can offload, get onto a certain level, and then you push another button to let the winder go down. So a winder is basically sort of a lift system for the miners and mining activities. So it's a huge system. It carries a lot of tons of weight. Whatever is mined is put in the same winder, it brings it up and offload somewhere. So these controllers that you're going to meet, which are the 2 types. we have to understand that when we look at a control circuit, no matter how complex it is, it must fulfill the following requirement. Meaning, if there's any fault, that circuit must fail safe. What that means is that when the circuit is dying or when the circuit is failing, it shouldn't explode. It shouldn't become a bomb where it explodes and kills other people. That's a failed design. So in a proper design, you're supposed to have a system that fails safe. That's one of the key points. Then the second one is that there mustn't be any sneaky circuits that can lead the system to malfunction. So once a circuit is properly designed, the components must ensure that there's no other purpose of those components. There's no other task that they are performing apart from the intended purpose. Then reliability, continuity under abnormal conditions must be there so that you don't have, it's easier for you to troubleshoot. So if the circuit fails safe, you can still test a few components and you can identify and troubleshoot and find which of the challenges that you are facing, which one is a problem. Then we must have minimum components. So if the circuit is designed, it must have a number of minimum components that make it functional. Because you must understand that there's a cost implication to all these devices. So you cannot design a circuit with many components that are doing one and the same function when you can have one to do those functions. So that's why we look at economic way of designing or economic way of handling circuits and designing of the circuits. Then the parts must be easily serviced, adjust, and replace. So you look at parts that you can find, parts that are easily replaceable, parts that you can stock in your storeroom, so that you have replaceable parts, and those are the parts that you're going to use. Of course, you can find unique parts that you require to use, but their uniqueness may be your downfall. In case that unique part fails and you can't get it and it's difficult to replace that part, then your whole circuit simply loses value or loses control. Then any circuit, any system that is designed must work according to its intended purpose. If it's supposed to operate a sprinkler, for instance, if it's a huge premise and it has been designed that this circuit has to operate sprinklers to spray water, maybe a farm, maybe a stadium, to spray water at a particular time, that system must work accordingly. It should not work in a way that it's supposed to spray water, but it starts switching off lights, it starts switching off other units and other systems that are not intended for that purpose. So these are critical things that you should go through later on when I share the notes. Go through and understand them. Now, when we come to the control circuit, we understand it from two basic circuits. One is what we call a two-wire circuit, okay? For instance, what you see here is a two-wire circuit. So the two-wire circuit operates in such a way that just as you have, for instance, a switch, a light in your house, you can have that is also a two-wire switch. So you have a switch there, and then you have a bulb. Okay, it may be a red bulb or a white bulb. So this is line 2, line 1. When you press this switch, current is going to flow through. Current is going to flow through. So let's say this is a current. Current is going to flow through from the left to the right, through this circuit, through this load, which is the light in this case, and back through the second line. So this basic circuit, switch circuit, is what we call a two-wire circuit. Why is it called a two-wire circuit? Because it's got two wires. This is wire 1 from this section to that section before the switching device. Okay, before any pilot device, you've got what we call a line 1. So you count the lines from there, that's line 1. And then from there to the load. So you've got a load, and this load in this case is a motor contactor. It can be a lamp as we have. So before the load, how many wires do we have? So here we've got 1 and 2, and this makes what we call a two-wire circuit. And so it usually uses maintained contacts. So if you look at this switch, it's a maintained contact where once it closes, it maintains itself. It holds on its own, just like a switch in the households that you have. This is not a contact that is operated or controlled by a relay or a contactor, but it operates and holds on its own. The other circuit that you will see is what we call the three-wire circuit. Okay, the three-wire circuit, which is here, operates on the principle of having, first of all, it has 3 wires, like I mentioned before the load. So this is the load. We have 3 wires counting from here. So you've got wire 1 before the stop button, and then there's wire 2 before the start button and the holding on contact. So this is considered as simply 1 wire. It is simply split here into 2, but it's 1 wire. Current will still flow in that direction and that direction to that section. And then from that start button and the holding on contact here, you've got wire 3. This is wire 3. So this one and that one is wire 3. So you've got 3 wires before the load. And this is a system that is very common in industrial applications, because why? You want to have the means of stopping, easier means of stopping the system. You want to have easier means of starting, and you want it to hold based on the motor contactor, so that if there's any fault, the motor contactor can open this circuit and the motor will stop running. So this is what we call a 3-wire circuit. And the 3-wire circuit is commonly used, but it's got the characteristic of what we call the auxiliary contact, this contact. Okay, this contact is mainly there to ensure that it holds the circuit running, because these push buttons, if you remember, they are spring loaded. So this is spring loaded. Once you push it, it will make contact here, but once you let go, it will release and no current can flow. So what happens is, as current is flowing, coming all the way up to here, when you push this button, once you push that button, it makes contact here, then current continues to flow, energizing the motor coil. And if you remember, the contactor coil is going to close, the plunger is going to move. Once it closes, all its normally open contacts will close. So this closes. And what will happen is that after you've released here, so here it goes back to its normal state, opens, and then current continues to flow through this closed contact to the motor contactor coil. So this is what we call the 3-wire circuit. So depending on the designs, these circuits can be used interchangeably. You'll find in some cases, you may be asked to design a circuit on which the two wire will suit you. For instance, a circuit that you can use a sensor to bring on a light, for instance, photocell can be used in this circuit. So you just, in place of the switch, you put the photocell there, and that photocell, once it closes, it will bring on the bulb, if you have the bulb as the load. You can also use motion sensors, okay? Motion sensor as part of the switching device here. Float switches can all be operated in a two-wire circuit, whereas in a three-wire circuit, you're going to have to use different sensing devices, mostly not connected direct here, but as you develop the circuit. Okay. Now, what you should note is that we can use a number of circuits when we design them in various designs. We can use those circuits to perform certain key functions, one of which is what we call interlocking. Okay, interlocking is where we use circuits to ensure that there is safety to personnel, also to ensure that there are no accidents. One does not accidentally press a reverse button, for instance, if the motor is running in forward direction, and also to just ensure that the coils can stand and withstand high voltage in the operation. So interlocking circuits are circuits that are used to guide and protect the system. So one of the interlocking circuits, we've got about 3 types of interlocking circuits. I'll leave these are basic definitions which you are going to go through, what a pilot control device is, what a primary control device is, and why we need auto transformers and so on. That we'll look at it later on. Now, when we look at interlocking circuits, we've got 3 types of interlocking circuits. One is the mechanical interlocking circuit. 2 is the push button interlocking circuit. And 3 is what we call the electrical interlocking circuit. Okay, when we come to this circuit, the mechanical interlocking circuit. So like I said, these interlocking circuits are meant to protect the contactor, to ensure that the contactor does not, or various contactors do not operate at the same time while the system is in operation. For instance, if a motor is running in forward, you don't want somebody to press reverse and it starts to run in reverse instantly. That is going to create overloading. First of all, the motor has got a inertia. It has to stop running and then reverse its operation. So these 3 types of interlocks ensure that there's safety, there's protection to the motors. And one of the methods that we use is to use what we call mechanical interlock. So if you look at this circuit, whenever you see a connection that shows dashed lines and a connection, this means these are mechanically connected. There's a mechanical linkage in between. So the operation of this circuit is to run the motor forward and reverse. Now, what happens is that if we press this to make sure that the motor runs in forward, once we press this, the coil gets energized, closes that circuit, and current flows continuously through there. But once this coil is energized, okay, once this coil is energized, what it does is that it makes sure that this stays in the de-energized mode. So it blocks this from activating mechanically. So the mechanical interlock blocks this contactor from being energized. Even if somebody presses this button, this is going to stay in the de-energized state. So it's not going to energize the relay here, or the contactor. It's not going to energize it. It will stay open. So current will flow, but this will not energize, and this will not close. For this reason, this will remain open. So the motor can only run in forward until somebody presses the stop button. Okay? So when you press the stop button, it's sort of a reset. So the stop button in this case operates as a reset. Resets the operation of the circuit. And then now you are able to start running the motor in the reverse. Now, when you press the reverse button, what happens now is that current flows through, energizing this contactor. And once you let go here, current continues to flow through that circuit while this is energized. But because it's mechanically linked with the forward contactor, then this will remain in the de-energized state. So that is the mechanical linkage, okay? That's the mechanical linkage that ensures that this is not de-energized even if somebody accidentally pushes the forward button. So that's the mechanical interlock. Then we also have what we call the push button interlock. You've got a question? I heard some microphone come on. Is there a question so far?
Tipo graça.
Oh, yes, what's your question?
Gurung saja. Oh,
Hello, what's your question?
si mic yangu je.
Anybody with a question? Okay, if there are no questions, then we'll move on to the next, to the push button interlock. And I'll ask you to mute your microphones so that we can okay.
Mic. Nziva pozimi.
So now let's look at the push button. Okay. Now, using the push button interlock, what we call the push button interlock has got what we call a brake make push button. Okay. So this push button appears as follows. I can zoom this so that you see it properly. So this is what we call a brake make push button. Okay. If you notice here, you will see that on this side there are contacts that are closed. Okay, normally closed, and on this side there are contacts that are normally open. So once you push it, this button, it breaks this contact and makes the other contact. Okay, this is what we call brake make push button. So it breaks this contact and makes the other contact. So these brake make push buttons are the buttons that are used in this circuit that we are looking at. So the circuit is this circuit. So what you notice here is that you've got, okay, thank you. Okay, we continue. So when you look at this circuit, what you see is that you've got a brake make push button here, which is linked. So the reverse and reverse is linked there. And then the forward and forward is linked there. So on one side, it is closed. On the other side, it is open. On this side, it is closed. On this side, it is open. So what is going to happen is that if I push the forward button, if I push this button, okay, current will flow through this circuit. Because this is normally closed, it will allow current to pass through it and energize the forward contactor. Once the forward contactor is energized, it's going to close there. Now you notice that the moment I push this one, the forward button here, it opens. So here closes and here it opens, okay? So once this opens here, even if at that moment somebody pushes this reverse button, it's not going to energize, okay? It's simply going to stop operation of the other circuit because it's going to open up here and cut that circuit. So, and then if you push both of them at the same time, this will open, that will close, this will open, and current will not flow through anywhere. It will end there and it will end there because both of these are going to be open if you push them at the same time. So if you push the push button interlock at the same time, nothing operates. So this is an interlock. Now on this circuit, there's all the three types of interlocks that we're discussing here. Like I said, the mechanical as well as the electrical, which we are going to look at next. So this is how the interlock operates for the push button. So it's just there to ensure that there is no operation if you press both of them at the same time. But if you press one, then one is going to run, while the other one is going to not run. You press the reverse, is going to run because this will open up and the forward will not run. Okay. Then the next interlock that we look at is what we call the electrical interlock. So in the electrical interlock, we are taking advantage of the contactors and their auxiliary contacts. We know that each contactor has got several auxiliary contacts, and we can use those auxiliary contacts. So we can use these auxiliary contacts by interchanging them into a different rung of the control circuit. So for instance, what we mean is that when you look at this circuit has got the forward contactor. Its auxiliary contact, the auxiliary contact for the forward contactor is placed in the rung of the reverse. So this, what it does, and you notice that it's normally closed. So what it does is if we push this button, which is the forward, it will close and the forward contactor will get energized because current flows through it. Once it is energized, it is going to close this contact, at the same time opens that contact, okay? Opens that auxiliary contact. So this implies that as current flows through, it will continue flowing in this circuit in that direction. But here, even if somebody presses the reverse button, current will flow through, but here it will be open. Current will not go through this section. current will not go through this section. Okay, this is what is happening here. So when we use the electrical interlock interchangeably, we can also use the auxiliary contact for the reverse contactor in the rung. This, we call these rungs. Let me just clean it up. We call these rungs. So you can count. This is a rung. There's another rung. So rung 2 and 1. So these, we call them rungs. So we're using the auxiliary contact of the reversing contactor in the forward contactor as normally closed here. So once we press this button, this closes, current flows through, energizing that contactor. This contactor, once energized, it will close that one and open this one. So even if somebody tries to push the forward button, it will not energize, current will not flow through this section because it is going to be open. So that's the principle that is being applied here as the electrical interlock. Okay, so these are the three main interlocking circuits. And then we have what we call motor reversing, jogging, inching, and indexing. Okay, so when we come to these reversing of a three-phase motor and reversing of a single-phase motor is very simple. So in a three-phase motor, you notice that the motor has got three phases: the red, yellow, blue phase, or line 1, line 2, line 3. And if we send, so all these three phases have got power to the motor. And if the motor is running in the forward direction, for instance, if we have got a setup where the motor is running in the forward direction, to reverse it, we have to interchange two of the conductors, as you can see here. Two of the conductors have to be interchanged in terms of direction. So line 1 goes to connect to terminal 3. Line 3 goes to connect to terminal 1. This interchange ensures that the motor is reversed. So if it's running in forward, once we interchange, this line connects to that one, and this line connects to that one. You interchange. Any of the lines can be used. Any of the two lines can be used to interchange. Once you interchange the two lines, then you are going to have the motor's reverse direction. For a single phase line motor, you've got the live and the neutral. So for a single phase, you just swap, and here you've got terminal 1, terminal 2. So you just interchange these lines. The live goes to terminal 2, the neutral goes to terminal 1, and the direction is reversed of operation of a single phase AC motor. So this is alternating current motors. This is how you can reverse their direction of operation. Whereas if we look at direct current motors, for direct current motors, there are two ways. One, we first have to interchange the armature current. So if we change the direction of the armature current and we leave the field current in the same way, then we can achieve change in direction of a DC motor. The other method is to change the direction of the field current. So these are the two methods that we use. So for DC motors, you've got two methods. You can interchange the field current, okay? Or you can interchange the armature current. Okay, so when you interchange the armature current by simply using contacts, for instance, for the forward, once this closes, what you are going to notice, if this is closed and that is closed, current is going to enter through this section and flow through in that direction, okay, in that direction, and go out from there. And then when these are closed, current will flow through that direction. And so this is the reverse forwarding of motors that are DC motors. Or you can change using reverse trigger circuits to trigger the reversal by simply changing the field current to the armature. And that also reverses. So you're playing with the field current here. Once you change the field current, you have reversed the DC motor. So that is how we reverse DC motors. In other cases, let me just clean up there. Okay, so that is what reversing is. Then we've got, I think I already mentioned this term, what we call jogging and inching of motors. Usually jogging is a special circuit that is designed to run the motor for coupling purposes. So you give it a jab of a full load current so that the motor runs and gets positioned in the actual position that you want. So this is a circuit that shows how we jog a motor. And this is done by adding what we call a brake make contact here in the jogging. So while you are installing the motor, you can give it a jab of direct current. So current to full load current. That full load current will pass through once you press this button to jog. In some cases, we use a selector switch, or you use a brake make contact a push button, which when you push it here, it will make contact and it will run the motor full of current without this closing. Okay, so it will jump, you can push it. It's like start stop. You start and stop it. You're just pushing it directly. Once it is aligned, you couple the motor, because each motor has got a coupling groove or a coupling positioning or aligning groove. So in that groove, when you're coupling a pump, you're coupling any other drive, a fan, or anything that is mounted to the motor, you can take advantage of the jogging in terms of coupling. Most of these cases are done because the rotor can be too thick, the rotor can be too huge to turn by hand, and you end up using this system of operation, which we call jogging. Okay, then I think this is all for today. I'll share this this handout. I'll share this handout through the WhatsApp to David, and then David will share with the whole class. Do we have questions?